So now we're going to talk about generalizing from the generic particular. So to show that every element of a set satisfies a certain property, you're going to suppose X is a particular but arbitrarily chosen element of the set, and show that X satisfies the property. So this is essentially an alternative to method of exhaustion. So you're going to take X represents some kind of particular, but at the same point arbitrary chosen element. X is, so it's like specific, but also you don't know what it is. So to explore this idea, I'm going to talk about this mathematical trick. I'm essentially going to do some magic with math. And so what I want you to do, I'm going to write down the instructions of the trick, but you should do the trick as I'm writing it down. So pick any number. So on your side of your paper, maybe write down a number. And what I want you to do after you pick that number, you're going to add 5 and multiply by 4. So add 5 to your number, then multiply your number by 4. All right, and then after you do that, you're going to subtract 6 and then divide by 2. And finally, I want you to subtract twice the original number. So maybe take a minute and do all of these steps. You're going to add 5 to your number, multiply that by 4, then take that and subtract 6, then take that, divide by 2, and finally you're going to subtract twice the original number, and I'm going to say your final number is 7. No matter what number you started with, I'm going to tell you you're going to always end up with 7, which seems really crazy, right? Because I just had you pick any number you wanted, do these sequence of steps, and you always end up in 7. So to see what's going on here, to verify that you end up with 7 always, you can think about this in 2 ways. So you can think about it in a visual way or an algebraic way. So we're going to look at both. So the first step is you pick a number. Now visually, your number is going to be represented by a box. But algebraically, we're going to think of using the variable x. And then what was our next step in this process? If you look, your first step was to take your number and add 5. So you're going to add 5. So I'm going to take my box and I'm going to add 5. So I'm going to use a vertical line for 5. 1, 2, 3, 4, 5. Algebraically, I took x and added 5 to it. So then our next step was to multiply by 4. So here you're gonna, if you multiply by 4, means you have 4 identical rows now. 4 boxes with a box and 5 ones. If we multiply by 4, algebraically, if we multiply by 4, we can distribute 4x plus 20. And then we subtract 6. So I'm going to take away 6 of the vertical lines. And because of our next step coming up, I'm going to take 3 away from the top row and 3 away from the second row. Here I take and subtract 6 algebraically. I get 4x plus 14. And then if you go back to your instructions, the next step was to divide by 2. So if I divide by 2 here, what's happening is 2 identical rows are shrinking into 1. So kind of like the opposite of the duplication we did earlier. So those 2 are identical, so they'll collapse down into a square and 2 boxes. And these are identical, so it'll collapse down to 1, a square, and 5 lines. So you're dividing by 2. You get 2x plus 7, which is exactly what we have represented in this picture. And then finally, you subtract twice the original number away. So that means you're going to remove these 2 boxes here. So I'm going to be left with 2 lines. Subtract 2x, and you're left with 7. So in the end, no matter what number you start with, you end up with the number 7. So we've just proved that this number trick always results in 7.